I'll start with this Euler equation again. So as you can see here, that here U, which is the internal energy or energy, is a function of S, V, N1, N2. So these N1, N2 are the species, are components 1, component 2, and these are the mole numbers, right? N1 is the mole number of component 1, N1 is mole number of component 1, and N2 again mole number. So these are N1, N2 and all. So you can tell that is like, if I have this, so we can tell S is the, so U is a function of S, S is entropy of the system, V is volume, and N, I, mole number of component I, right? Now, as we know from this, because U is a function of SVN and U is also homogeneous, we have just discussed in the previous lecture, it's a homogeneous first order function, and lambda is an arbitrary multiplier. That is greater than 0. Okay, so now if you have this, so you lambda S, lambda V, lambda N1, lambda N2, that means each of these extensive parameters on which U depends on are multiplied with this multiplier lambda. This becomes equal to lambda times, and lambda to the power 1 times, lambda to the power 1 is basically nothing but, lambda to the power 1 is nothing but lambda. Lambda times U, S, V, N1, N2, so on. Now, here I do something very interesting here. Instead of differentiating with respect to, say, in general what we have seen, we have differentiated with respect to S, we have differentiated with respect to V or N1 or N2. But here what we are doing is, we are differentiating with respect to lambda. Differentiate with respect to lambda. Now if you do that, so using chain rule, what you can write, del U, then you have this, all this lambda S, lambda V, so on, del U, and now we are basically, say, differentiating with respect to lambda S, but we are actually we are differentiating with respect to lambda. So how do I do that? So I can write this way, as I have written here, it is del U, del lambda S, del lambda S, del lambda, right? Again del U, del lambda V, del lambda V, del lambda, and so on, which is going to be, if I differentiate here on the right hand side, it is del lambda U SVN del lambda. Del lambda, del lambda, basically it's 1, right? So this, if I do differentiating lambda with respect to lambda, will give me 1, right? Unity. So as a result, here we do not have lambda, right? Here it is 1. So now you have U SVN1. So if you look at the right hand side, and on the left hand side, we are differentiating with respect to lambda, and we are using a chain rule, right? So del U, del lambda S, del lambda S, del lambda, del U, del lambda S, del U, del lambda V, del lambda V, del lambda, del U, del lambda N1, del lambda N1, del lambda, so on and so forth, right? So that is what we are doing. So basically, if I have, say, only one component, I can show you. So this is nothing but, what we are writing is U, lambda S, lambda V, and you have one component, say lambda N1. equals to lambda u is v. And now differentiate, so you write with respect to lambda. So del u del lambda s del lambda s del lambda plus del u del lambda v del lambda v del lambda plus del u del lambda n del lambda n del lambda equals to u s comma v comma, right? Because since del lambda and whatever with this lambda u equal to nothing but u, right? Del lambda is nothing but u itself, so, right? So that is why you have u as vn here. Now once you have done that, this equation, because it's an arbitrary multiplier, we can take it is true for any lambda. It is true for any lambda. So this differentiation that we are doing is true for any lambda. So put lambda equal to 1. So what do you get? Del u del s into s, right? Because del lambda is, so this is the point. So if you write del lambda s del lambda, this is nothing but s, right? Similarly, del lambda is u. So you have, if you have that, this is this. So it's clear. You see from the first term, if you look at this term, then from here you get this del u del s s, del u del v v, and then del u del nj nj, right? Or del u del n1. So this, as I told you, that it is like for each n, which is j starts from 1 to r, right? So you have r components, and so it becomes del u del nj nj equals to u. So what you can write now is u equal to ts, right? Del u del s is t, right? Del u del s. When I am talking about del u del s, remember what we are telling is that v is constant in n, all the n1, n2, all for all components, small numbers are constant, volume is constant, then del u del, so del u del s is nothing but t, right? So del u del s is nothing but t, and del u del v is minus p, right? And del u del nj is, del u del nj is mu j, right? So you have mu1 n1, mu2 n2, mu3 n3. So now you get a very, very useful relation, that u equal to ts minus pv plus mu1 n1 plus mu2 n2 plus dot 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 mu r nr. So up to r components. Now with this relation, if you have that, you also know from this exact differential, because du is an exact differential, du is tds minus bdv plus mu I dni. But from the Euler relation, what you get is u equal to ts minus pv plus mu I ni. Now if I use Euler relation, that is if I use 2, right? If I use this relation, then I can write du equals to tds plus sdt minus pdv minus vdp plus mu I dni plus ni d mu I. See, this is coming from 2, right? Because, say for example, if I write u equal to ts, then du equals to tds plus sdt, right? Similarly, minus pv, if I have two variables, right? P and v. So this becomes minus pdv minus vdp. Then again I have plus mu I and I. So, and again mu I and I is repeating, and we are summing over I goes from 1 to r. So this becomes sum mu I and I equal to 1 to r. Now if this is so, then we can write this as plus summation I equal to 1 to R Ni d mu I plus mu I dn. Now compare. If you compare, you have mu I dni already, right? In equation 1, you have mu I dni, but there is no ni d mu I, right? So if I look at 3 and look at 1, so 1 and 3, if I compare this one with this one, compare this one and this one, then immediately I can see that s dt, right, this term s dt minus v dp and ni d mu I, these are coming extra, and so s dt minus v dp plus ni d mu I have to be equal to 0, and this is called Gibbs-Duhem relation. This Gibbs-Duhem relation I am writing for you. I can write similarly for G or H or Helmholtz free energy, some of these which we have defined earlier. So now we will try to understand how are these related, how are these different thermodynamic potentials related. So you have U, you can write U as a function of S, V and N, U as a function of S, U as a function of S, V and N. Similarly, you can write S as a function of U, V and N. And then there are also other thermodynamic potentials that can come in. How are they coming? Right? You can define other thermodynamic potentials. For example, what are the different thermodynamic potentials we have defined? We have defined, for example, H equals to U plus PV. Then we have defined G equals to H minus PS. Right? So you have defined H, you have defined G, and then if you have defined F, right? Helmholtz free energy. How do you define all of this thermodynamic? Helmholtz free energy, Gibbs free energy, enthalpy. How are you defining this? Means what's the basis of defining this? So you will see soon how we define such different functions, right? How are they related, right? So G equals to H minus Ts, F equals to say F equals to U minus Ts. So different formulations or different thermodynamic potentials can be used to describe basically the energy of the system. So in one case we call it internal energy, in one case we call it Helmholtz free energy, in one case we call it Gibbs free energy, right? All of these, how are they related, right? So we want to see that, right? So obviously we know how are they related, but how are these relations coming, and what is there a fundamental connection between all of these, right? Is there a commonality between all of these, or can we define any type of thermodynamic potential that we want to? So we will look at that. But before that, one very important point that we have talked about. See, we have talked about that you can do either of ds equal to 0 and d2s less than 0 for maximization of entropy, or du equal to 0 and d2u greater than 0 for minimization of energy. So this tells entropy maximum principle, and this is energy minimum principle. However, we have also discussed that when we do the second one, we are keeping the total entropy of the composite system constant. In the other case, we are telling the total energy of the composite of the simple composite system constant. So here we are, so basically if you look at the principle, the equilibrium value of any unconstrained internal parameter. So unconstrained internal parameter can be U, it can be S. So in this case, this it can be V, N, all this. So basically the equilibrium value of any unconstrained internal parameter. This unconstrained internal parameter example is like V alpha, V beta, then say for example N1 alpha, N1 beta, U alpha, U beta, if you take say two subsystems alpha and beta, is such as to maximize the entropy for the given value of total internal energy. That means total internal energy is given or fixed, right? Given value means it's fixed, total internal energy is fixed, and we are telling the equilibrium value of any unconstrained internal parameter. Unconstrained, again constant is put by wall, right? Unconstrained internal parameter means where we are allowing the subsystems to exchange energy, exchange matter, and we also perform mechanical work, that is redistribute volume. All of these, if we are telling, that means we are completely relaxing all the internal relaxing all the constraints that are imposed by the wall, right? So we are making the wall diathermal, we are making the wall flexible, we are making the wall permeable to exchange of species, right, between subsystems. So in such case, the equilibrium value demands the entropy to be maximized. But energy minimum is telling you exactly the same statement in this way, that equilibrium value of any unconstrained internal parameter, again the same set of unconstrained internal parameters or maybe slightly different. So for example, the internal parameters are same V alpha, V beta, and then you have N1 alpha and N1 beta. But now you have S alpha and S beta, right? So if you look at that, the equilibrium alpha of any unconstrained internal parameter, again unconstrained means the constraints that we impose by using a wall, we are lifting these constraints. So that means we are making the wall flexible, we are making the wall diathermal, we are making the wall permeable to exchange of species or exchange of matter, is such as to minimize. So in this case, say for example, let us look at the contrasting words. Here it is maximizing the entropy for given value of total internal energy, and this is minimize the energy for the given value of total entropy. Now from Gallen's book, this is we haven't reproduced, I have drawn it, I have redrawn the diagram, but the idea is this is your surface, this is your energy surface. For example, this is the S as a function of, so what you have drawn here essentially is S as a function of U and all other parameters like Vn. So instead of that I am writing it as S, U and all the other parameters Xj, right? So this surface, now if you see this plane, the plane that I have drawn here, see U, this is the U axis, this is the S axis, and this is the Xj axis. Okay, so this axis is Xj. Basically, you see it's like a multi-dimensional surface, but we are telling that this axis contains all the Xj. So if in that case, what we are telling is, when you are drawing this plane, as you can see here, what we are telling is that we are fixing in the U axis, we are fixing a plane, right? That means we are fixing the value of U and drawing this plane. This plane intersects the SUVN surface, and the way it intersects is this. Means if you see the diagram, you will understand easily that for this value, the equilibrium will be obtained by maximization of entropy. Now look at the same surface. Now instead of look at the same surface, but you take a plane of fixed entropy. Fixed entropy, you can immediately see, is basically indicating there is an energy minimum here, right? You are seeing the section here. So I am talking about fixed entropy plane. In the other case, I am talking about a fixed energy plane. Fixed energy plane, there is entropy maximization, right? Entropy is in this axis, right? So entropy is maximized, right? If you look at this curve that is made by the plane, you can immediately see from the shape that is the maximum. Now, more formally, you can prove this. How do you prove this? You want to say for example, how do I prove one from the other? If I assume that entropy maximum principle is indeed true, then I should see that from entropy maximum principle, we can get the energy minimum principle, or vice versa. Now that is what we are going to do now. So as you can see, I started with the entropy maximum principle. So when I talk about entropy maximum principle, we are basically telling S is a function of U, that is the energy of the system, volume of the system, and mole number of components that constitute the system, right? So basically this U, V, N, so V and N I am substituting by Y. So Y represents V, N1, N2 and all other such variables. Like if we have multi-component, so we have N1 mole number of component 1, N2 moles of component 2, N3 moles of component 3 and so on, right? Now what we are telling is S is a function of U, right? S is a function of energy and other variables like V, N1, N2, which we are lumping into this variable Y, right? So the Y basically contains all these variables V, N1, N2 and so on. Now let us assume, say S is a function of, so for example, let us assume instead of lumping all variables, if I tell that okay, it is a one component system and S in that component system is a function of U comma V. Okay, so we are thinking of S is a function of U comma V. Okay, and maybe you have one component and that component mole number is always fixed. So I am not taking U comma N and here again U comma N. So I am neglecting this N completely just for the ease of notation, right? So you have now in this case what we are assuming is the extremum condition for entropy or maximization of entropy. If I am considering maximization of entropy, first thing, the first derivative of entropy with respect to volume, right, is a function of U and V, keeping energy fixed, right, for a given internal energy, right, keeping energy fixed, as you can see, has to be equal to 0. And another, now this is the extremization condition. Now this extremum has to be a maximum, so we have to look at the second derivative. The second derivative tells you del 2s del v square, del 2s del v square for the same fixed internal energy has to be less than 0. That means it has to be negative. If it is negative, indeed it is the maximum value. So we are maximizing, right? So as you can see here, that we know that del u del v s, right, del u del v s is equal to minus p, right? Now we are trying to look at, so we know del s del v, we want now assuming this, assuming the entropy maximum principle for a given internal energy, I want to prove the energy minimum principle, that indeed it leads to this energy minimum principle. So in the energy minimum principle, again what we are writing first, U as a function of S and V, and now I will try to find out del u del V, right, del u del V as a function of S. Now del u del V as a function of S should be equal to, so this means for a fixed entropy, right, this means fixed entropy, right? For a given entropy, we are trying to find the derivative of U with respect to change in volume, right? Del U del V as a function of with fixed S or for a given value of S, right? And we will try to find out that whether it is 0, right? So now as you can see, del U del V S is equal to minus P, right? Because del u del Vs is into dV, so it is minus P dV. So del u del Vs is definitely equal to minus P. Now we can write this as this del u del Vs. Look at this term. We can write this as del S del VU. So we have discussed different types of the partial differentiation formula, and you can see that one of the ways to write this is basically you take del S del V, so S is your fixed quantity, but here we are writing in terms of U and V as fixed quantities, so we can write this derivative, this one, in terms of a ratio of del S del VU and del S del U V, right? And there is a negative sign here. So this is something you can basically prove, and I can show you that it is indeed it is possible to prove this. This basically you have Z as a function of X and Y. Now if you have that, what you are telling is basically del Z del Y times del Z del Y times del X del X del Z del X. So you will have X here. So del X del Z. See, it's nothing but a chain rule, del X del Z, and this will be, so del Z del Y del X, and this will be del X del Y, right? So this indeed will be equal to, so del Z del Y del X del Z del Y del X, this goes to -1. This is something that we have shown previously, right? We have shown this relation, right? So del Z del Y times del Z del X del Z times del Y del X will be equal to -1, right? You can try to derive this. So if you derive this, then we can basically see that del Y del X, which is nothing but an inverse of del X by del Y, right? If we use that, then del Z del Y is nothing but minus of, if you see, now both terms go up, so you have here it is del X by del Z, and this is del Y by del X below, so this becomes del X by del Y. Now when I do del X by del Y, what is fixed? Z is fixed. When I do del X by del Z, Y is fixed. So exactly this is the one that we are using here. So if we use this relation, then what we basically get is minus del S del V U for a fixed U and minus del S del U V. Now note that del S del V U is something for entropy maximum principle is equal to 0. Del S del V U is 0 and del S del U V is nothing but 1 by T, right? Del S del U V is nothing but 1 by T. So 1 by T is basically T, and there is a minus sign. So minus T del S del V U, and del S del V U according to the entropy maximum principle, which we have taken to be true, right? We have assumed entropy maximum principle to be true, and what we want to prove is entropy maximum principle implies energy minimum principle, right? So immediately, so this is equal to 0, so this is equal to 0 because we have assumed the entropy maximum principle. So del S del V U equal to 0 is given, right? So from our assumption, right, from our earlier assumption of entropy maximum, so we can now see that del U del V S is indeed 0 if del S del V U is 0. That means change in entropy with respect to change in volume for a given internal energy equal to 0 implies that change in internal energy with respect to volume for a fixed entropy to be also equal to 0, right? Which is an extremum condition now, which is an extremum condition for U, right? Del U del V S equal to 0 is an extremum condition. Now, whether this extremum condition basically leads to an energy minimum principle, what we have to prove? We have to prove that del 2U del V square for a given S is greater than 0, right? So, this is what we want to do. Now, del 2U del V square is nothing but minus of, if you see this, del U del V S is minus P. So, del 2U del V square is nothing but minus del P del V S, right? So, which is equals to minus del P del V S. Now, this is going to be written as minus del P del V U. how does this come, right? So think about it and try to derive it. So now see, I will derive this, but see, first I start with del P del V S. So I am starting with del P del V S. Now del P del V S is nothing but del P del U V del U del V S. Again I am using a chain rule. So I am using the chain rule, del P del U V del U del V S, and plus, right? So P is a function of U and V. So think of this. P is a function of U and V. We are assuming, because see, this is one equation of state, right? P is a function of U and V, right? So what I am writing here is dP. So basically, let's see, equals to del P del U V du plus del P del V U dV, right? Now what we are doing is we are differentiating this, the left hand side and right hand side with respect to V, right? So this becomes del P del V. So now this implies del P del V. When I do del P del V, what I am fixing is S equals to del P del U V is remaining, and this becomes del U del V S. So del P del U V and del U del V plus del P del V U, and this is del V, which is basically del V del Vs, right? This becomes del V del Vs, so which is basically equals to 1, right? So now what you have, del P del U V. So what you have here is del P del U V del U del Vs plus del P del V, right? Now you see del U del Vs, right? Del U del Vs, we know del U del Vs is minus P, right? Del U del Vs we know is minus P, right? So I am writing minus P del U. Now del P del U, again here we have put V here, and this is del P del V U, right? Now, which is nothing but del P del C. Now minus P is equal to 0, right? Del U del Vs is equal to 0. So basically P equal to 0. If P equal to 0, right, from the extremization condition for U, right, del U del Vs, which is minus P, which we found that for energy minimum principle, first thing is the energy extremum, which is indeed equal to 0, right? And if this is equal to, if we assume the entropy maximum principle, then del U del Vs is equal to 0 or minus P equal to 0. So if minus P equal to 0, this term goes off. So we have del P del V U. So we have proved then that del P del Vs equals to del P del V U, right? Del P del V U, fixed energy, right? So at P equal to 0. P equal to 0 means del U del Vs equal to 0. Now this means now del P del V U can be written as del V of, so you can just look at this. So this becomes del P del V U, right, at P equal to 0. Now I am writing del V, and P is del U del Vs, right? So del U del Vs I can write as del S del V U. Again you can prove this, but there is again a minus sign here, right? There is a minus sign here. Note here that there is a minus sign, right? And you can again prove that minus sign again using the relation like this, right? So if you have that, if you have that, you have del S del V U, you have del S del U V, and there is a minus sign here. which is minus, now because if you see here del S del U and there is del S del V, right? So if you look at this, it is nothing but del U del V, right? In some sense it is, you can immediately see here that this is del U by del V, which I am writing in terms of this del S by del V and del S by del U, again using the relation, the chain rule that we have proved with a minus 1. Remember that has minus 1. If I multiply, then we will basically get minus 1. So then del V of this entire stuff. So basically, if that is so, we can now again use the product rule. If we use the product rule for partial differentiation, then del V of del S del VU, keeping del S del U V as constant, so we have the minus sign, and this becomes del V of del S del V is nothing but del 2S del V square, and here this becomes del S del V U I am now fixing, and so this is del V of minus 1 by del S del U. So this is going to be del S del V U and minus 1 by, so minus 1 by x if I have, so the differentiation, so basically it's like minus of 1 by x, so it will be minus of, if you do del x of minus of 1 by x, basically you get minus of, so if you just do del x of 1 by x, this is equal to minus 1 by x square, right, because it is x to the power minus 1, so minus 1 x to the power minus 2, which is minus 1 by x square. Now if I put a minus sign here, then there is a minus sign already from the derivative, so minus and minus becomes plus. So it is del S by del U squared, and above it is del 2S del U del V, right, del 2S del U del V. Now if you see this, you have del S by del U, del S by del U is 1 by t, so this becomes minus t del 2S del V square, but here del S del V U, right, this is something that from the entropy maximum principle we have already told del S del V U is equal to 0, right, del S del V equal to 0 means this entire term goes to 0, and so you have minus t del 2S del V square, right, minus t del 2S del V square, and del 2S del V square is less than, we also know, since del 2S del V square from entropy maximum principle is less than 0. Therefore, so basically del 2S del V square is negative, minus t, so this, there is a minus sign, negative sign here, and t is positive, right. So this term, what is this term? The term that we are talking about here is del 2U del V square S, right. So this is basically what we are trying to do is del 2U del V square S. Equal to this term, which comes out to be, right, which is equals to, coming out to be minus del P del VU, first of all it is minus del P del Vs, but we have proved that it is minus del P del VU, and minus del P del VU again we are writing it this way, and then we basically get from entropy maximum that this term del S del VU equal to 0. So you have minus t del 2S del V square, and as you can see del 2S del V square is less than 0 from entropy maximum principle. This makes this negative, this is also negative, t is positive, so this has to be greater than 0. Therefore, u has to be a minimum, right? The experiment condition is, so basically we have proved two conditions here. We have proved that given del S del VU equal to 0 and del 2S del V square less than 0 for a fixed energy, implies that del U del Vs, that is for a given entropy, the partial derivative of u with respect to V is equal to 0, and del 2U del V square is basically greater than 0. Del 2U del V square for a fixed entropy is greater than 0. That means entropy maximum principle implies energy minimum principle. We can show it graphically, we can show it otherwise, right? We can also prove the other, means we can assume energy minimum principle and prove the entropy maximum principle, right? So that means these are equivalent and interchangeable. In the case of entropy maximization, we keep the energy fixed, energy of the system fixed. In case of energy minimum principle, we are keeping the entropy fixed, right? Total entropy of the system to be fixed. Now comes one very interesting thing, means I won't go into the detail. If you want to go into the detail, you can look at Callan or some other book like Callan, right? Or some modern books that use the treatment of Callan. So where we come to this interesting transformation in math, which is called Legendre transformation. The idea of Legendre transformation is this. If you have a function, in general, how do you write a function? Say y equals to f of x or y equals to y of x. So y is a function of x. This means y is a function of x. Now how do you plot it? So you have some graph, say for example, you have y in the y-axis, so y is varying, and here x is varying, so you have x varying this way, and this is your curve, right? And you basically, this curve represents y as a function of x, right? This can be written, the same curve can be written as a function of a tangent to this curve, which has a slope, right? Which has a slope and intercept. The intercept is basically psi, right? Psi is the intercept, and right, 0 comma psi means this is equal to psi, and p is the slope. Now, as you can see here, you look at this line, you have drawn a tangent at some arbitrary point x comma y, and you have the intercept which is basically 0 comma psi. Then immediately you can see p, the slope is basically y2 minus y1 by x2 minus x1. So, right, the slope dy dx is nothing but y2 minus y1, well, this is simple coordinate geometry, by x2 minus x1, which is y minus psi by x minus 0, or psi equals to, so if that is so what does this mean? P equals to y minus psi by x, or psi equal to so I have taken px, so this becomes y minus px, right? Because I am taking x to the left hand side, so it becomes px, and you have psi here. You take psi now here, so px comes to the right hand side, so y minus px. So psi equal to y minus px, right? So basically, if you have this, so what we have done is basically we have used now one relation, which is psi equal to y minus px, which is the intercept, right? So let's write this way, psi equal to y minus px is the intercept, right, on the y-axis. So it is the intercept, and p is nothing but the slope. Now if you see that, so you have dy by dx is equal to p, right? So dy equals to p dx, right? That's why dy equals to p dx. So d psi is equals to dy minus p dx, right? From this equation you can write d psi equals dy minus p dx minus xdp, right? So this is the thing. So now dy minus p dx minus xdp, right? Which is equal to minus xdp. Why is that so? This is because dy, so dy dx equal to p, dy by dx equal to p implies that dy equals to p dx. But if I write d psi, which is dy minus p dx minus x dp. So we have this extra term. So this term, this guy is to go to 0. We have minus x dp. So you have d psi equals to minus x dp or minus x equals to d psi by d. Right? So you have minus x. So let us write this way. Minus x equals to d psi by dp. Right? And you have also psi is y minus px. Now if you see that, it is possible to write this entire curve. The idea is this: it is possible to write or express this curve as a function of psi and p. That means it is as a function of intercept and slope. This is indeed true because if you do this series of intercepts and slopes, if you write a series of intercepts of slopes, so you see, if I draw a series of intercepts and slopes, then basically this curve comes as an envelope, right? So this different, so I am basically adding the intercepts. So I have intercept here, here, here. So for each, and then I have different types of tangents. So I can go on drawing a series of tangents. What I am describing from the envelope is the curve itself. So basically, what we are telling, the usual form that we write y is a function of x can be written in terms of the slope and the series of slopes and intercepts of the curve, right? Basically, the slopes and intercepts made by the tangent point, right? Made by the tangent to the curve at different points, right? You have a series of tangents that you can draw on the curve, and using that series of tangents, these tangents are described by their slopes and intercepts, right? The tangents are described by slopes and intercepts, and you have this series of tangents. So basically, the series of tangents, the envelope represented by the series of tangents, and the series of tangents are characterized by their slope and their intercept, because tangents are straight lines, right? So using the series of tangents and the inner envelope described by it, we can basically define an alternate form of the curve in terms of psi and p. This is something that becomes very, very useful when you define different thermodynamic potentials like Gibbs free energy, Helmholtz free energy, and so on. Basically, what I want to show you is this, that T and S are conjugate, V and P are conjugate, then mu and N have conjugate relation. So all of these we can basically show if we apply a transformation like Legendre transformation. However, here we are talking about a single variable Legendre transformation just for the purpose of demonstration. But ultimately, you can do it for multiple variables, and you can do this. Basically, you have a curve which is given in the form z as a function of x and y. Now you write the same curve in terms of tangent planes in the case tangent planes. So if you write that, then basically you are representing it in terms of slopes and intercepts made by the tangent, right? So that's the idea. So more formally, you have y as a function of x, and from there you have y as a function of x. From there you can define a slope, which is dy dx, and intercept, which is minus px plus y. Now you see, using these two, I can eliminate x and y and get psi equals to psi p. Now inverse Legendre transformation is psi equal to psi p. Again, I can write minus x equals to d psi dp and y equals to xp plus psi, right? Y equals to xp plus psi, and now I have these two equations, and I eliminate psi and p, and I get y as a function of x. Right? Now, if I think of that, now very intuitively you can immediately realize this. See, you have u as a function of s, v, n1, and so on. Now you want to replace s by its conjugate, which is t, and t is nothing but del u del s as a function, del u del s, keeping v and all other components, mole numbers constant, right? And f, which is an intercept, of what? U minus T. T is the, right, U minus Ts. See, F equals to U minus Ts. It immediately comes in. Now, if you do this, you eliminate U. So, you have these two relations. You eliminate U and S from these two relations to get F as a function of T, V, right? It is a function of T, V, N1, right? So, if V, N1, we are not changing anything, right? So, only thing that we have done is T equals to del U del S and F equals to U minus Ts, which is the intercept. And I am writing now in terms of intercept and slope, right? Intercept and slope. So, F is a function of T, V, N1. And here we are writing, if I write F as a function of T, V, N1, now S, as you can see, is minus del F del T, right? S is nothing but minus del F del T. How does it come? You have F here. Now, if you do del F del T, then basically what you get is minuses, right? You get is minuses. So, S equals to minus of del F del T and U is equals to F plus Ts, right? Now, elimination of F and T gives you U as a function of SV, right? So, the way to understand this is very simple. So, you have U as a function of S, V, N1, then R. What you are writing is a new definition, which is U minus Ts, which basically is replacing U by F, right, which is basically an intercept U minus Ts, right? We have seen F equals to U minus Ts and S is replaced now by T, its conjugate, and V, N1 to N, right? So, this is a Legendre. So, basically F is a Legendre transform of U where the slope del U del S, right, del U del S is replacing the original function S, right. The slope del U del S, which is nothing but temperature, is replacing the original function S, right, and F is defined as the intercept U minus Ts, right. So, now if that is so, we can write df, you can write. So, why we do this? So, why I have done this is because to make you understand that basically since this conjugate relationship exists and we can use this Legendre transform where when we are replacing the curve U equals to a function U as a function of S, we are replacing in terms of F as a function of T. So, basically F as a function of T, the advantage here, there is a big advantage here. See, in case of U as a function of S, you have to also define equations of state, right? Which where T is a function of, see, when we write this way, energy minimum principle, you have U as a function of S, V, N1, Nr. But you also require a relation, which is T, which is a function of S. So, it's a homogeneous zeroth order function of all these extensive parameters, right? You require all of this. Now, these two can be replaced now by a new thermal potential F, which is directly a function of T, V, N1. So, you don't require this additional relation or this additional equation of state, right? You do not require this equation of state in this case. If you consider that you have a system with fixed volume and mole number, and this system is in contact with a thermal reservoir, right, or a temperature reservoir. If you have that, then basically you are telling that the system will assume the temperature of the reservoir, right? It will become based on thermal equilibrium, because reservoir is like an infinite reservoir of temperature, right? So, if there is a small change in U in the reservoir, it does not change T of the reservoir, means the temperature of the reservoir. So, according to thermal equilibrium, the system will assume always the temperature of the thermal reservoir that it is in contact with, right? So, as a result, we are now making this equation, means basically we are telling that this equation of state is no longer required. We can directly use in such a case the minimization of f instead of minimization of u. When I do minimization of u, I require this equation of state to be supplied, but if I do minimization of f, only thing that we are talking about is that the system is in contact with the thermal reservoir. So as you can see now, the equivalence between u and f. So u as a function of s is replaced by f as a function of t, right? Vn1 remains Vn1. Similarly, we can define h. H is a function of, so u as a function of s, Vn. Now what we are doing is s remains, we do not touch s, but we are touching the another slope, which is del u del v, which is minus p. So h is written as a function of s, but v is replaced by its conjugate, right? And then we have n1 into so on. So minus p equals to del u by del v, and h is nothing but u plus pv, right? H is the intercept, which is u plus pv. So as you can see, h is the intercept, p is pressure, which is the slope of del u by del v, and u is your original function, right? U as a function. So this is your y as a function of x, which is now replaced by psi as a function of p, right? P is the slope here, right? So h becomes a function of s, p, n1, and so on. Now, if you see the inverse Legendre transform is, you are given h, but you know v, which is nothing but del h del p, right? V is nothing but del h del p, and u, which is nothing but h minus pv, right? So v is del h del p, u is h minus pv, because h equals to u plus pv, and then you eliminate h and p, and you get back u as a function of s. Now again, if you do u as a function of s, v, and you want to basically minimize, again you require p, you require here the relation of p as a function of, if you would have done directly with u or minimization of energy, then p as a function of s, v, n1 was required. However, now if we think that we have a pressure reservoir, basically a pressure reservoir is such that there is a wall between the system and the reservoir, and the wall is flexible, but the change in, whatever be the change in volume, there is no change in pressure, right? The pressure in the reservoir is kept constant, right? The pressure, there is no, because the change in volume is so infinitesimal in terms of, when you consider this infinite reservoir, then basically what we are telling is the pressure inside the reservoir remains unchanged. So obviously the system will assume the pressure of the reservoir as because of mechanical equilibrium, right? Now in that case, I can directly use dH or extremization of dH, which does not require another equation of state, right? When you do minimization of energy, you require an equation of state which relates P to the extensive variables as V, N. However, if I use directly H, then I am only considering a pressure reservoir, right? We are considering a pressure reservoir, and as a result, we eliminate the need for this equation of state, right? Now comes one very important function. We have already defined it. We can see all of this means all this exercise is done to make you understand that all these thermodynamic potentials are related by a very simple transformation, right? By a transformation called Legendre transformation, and as a result, all of these are connected, right? So it's not like means there is the connection is very mathematical, and we can basically look at these different types of principles like entropy maximization principle or energy minimization principle, which requires the equations of state. But using these transformations was useful because instead of using S and V, right, S and V, if I can replace S and V by their conjugate, like S conjugate is T and V's conjugate is P, then I can think of a thermal reservoir, I can think of a pressure reservoir, right, a mechanical reservoir. So if I am thinking of that, then basically See, for example, if I am doing that, so basically there are two slopes, t, which is del u by del s. In this case, t is del u by del s is the first one, and then there is minus p, which is del u by del v, and we are writing g as u minus ts plus pv, which is nothing but h, u plus pv is h, so this is h minus ts. So now if you see, you have three equations, and you have u, s and v. If you eliminate them, then you get g as a function of t, p and n, right? And again, if you have that, you can write dg equals to minus s dt plus v dp plus mu 1 dn1 plus mu 2 dn2. Now you can see here, so this is something that I just want to tell you, dg equals to del g del t, and this becomes p n1 dt, and del g del t is nothing but minus s, right? Del g del t is nothing but minus s, and then you have del g del p, and in this case this t is constant fixed and n1 and nr, and you have p, and then you have del g del n1, and t and p are fixed, and n2 dot dot dot. So basically, and d, so and so on. So this becomes del g del 1, del g del t is nothing but minus s, del g del p is nothing but del g del p is nothing but v, and del g del n1 is nothing but mu 1, right? So mu 1. So this is one relation. Second, like we defined the Gibbs-Duhem relation when we talked about the Euler relation, and the Gibbs-Duhem relation we have given in terms of u, right? But for g also I can write another Gibbs-Duhem relation. So g is u minus ts plus pv. So dg can then be written as du minus tds minus s dt plus pdv plus pdp. Now one term is missing, so plus it will be mu n. Missing because we have neglected that, right? We are not concerned with that, but here definitely there is a g u minus ts plus pv plus mu n, right? Because we are not replacing mu with n, means we are not using any conjugate relation between mu and n here, right? So when you are defining g, so mu n remains as mu n. So this becomes plus mu dn, mu I, so you can write mu I ni, so mu I dni plus ni d mu I. But again, if you look at this relation 1 and this one 2, immediately it follows from that du minus tds plus pdv plus, right, du, so minus sdt plus vdp remains, du minus tds plus pdv plus mu I dn plus ni d mu I. Now du plus pdv from first law, you can see du plus pdv means combined first and second laws is nothing but tds, right? Du plus pdv minus tds basically cancels out. So you have ni d mu I equal to c, right? That is the Gibbs-Duhem right? So we have done this Gibbs-Duhem relation. Here again you can see that we get back the Gibbs-Duhem relation ni d mu I equal to 0. from the definition of G. So this gives free energy minimum principle or potential Helmholtz potential minimum principle. You can see that the equilibrium value now of any unconstrained internal parameter in a system in diathermal contact with a heat reservoir minimizes the Helmholtz potential over the manifolds of states for which T of the system equal to T of the reservoir. In the case of Gibbs free energy minimum, we are telling the equilibrium value of any unconstrained internal parameter in a system, right? Any unconstrained internal parameter in a system, it can be like different mu's, right? In contact with a thermal and pressure reservoir minimizes the Gibbs free energy at constant temperature and pressure. Basically, T assumes the temperature of the reservoir, which is T equals to TR and P equals to PR. So basically, if you see this, du plus ur equals to du minus TR ds plus PR dv, which is equal to 0. Right? You can it follows this way. Let's see, d of what we are telling here is the system plus reservoir is your universe, and so you are telling du plus ur has to be 0, and du2u plus ur, where ur is basically the energy of the reservoir, which you can tell that it is fixed, right? Because it's an infinite reservoir. So basically d2u is greater than 0, subject to that S plus SR is basically fixed, right? This is what we are basically doing. Now if you do that, it follows, you can easily see that it follows that dg has to be equal to 0 and d2g has to be equal to d2u, which has to be greater than 0. Right? So let us assume, let us understand why it is so. Say for example, let us start with system at constant temperature in contact with a reservoir. Now system plus reservoir is one isolated system, right? System plus reservoir is one isolated system where delta u plus ur equals to 0, where u is the internal energy of the system and ur is the internal energy of the reservoir, right? You have ur, which is the internal energy of the reservoir, and you have u, which is the internal energy of the system, and we are also telling that there is a change in entropy, right? Delta S plus delta SR, which can be equal to 0 for reversible processes. Delta S plus delta SR can be equal to 0, or it has to be either equal to 0 or greater than 0, right? Now, one of the assumptions when I am talking about a reservoir, when I define a reservoir, size of the reservoir is infinite compared to the size of the system. Right? That's what we are telling, right? There is a very infinitesimal change. So, nothing basically changes. Even if there is some change in terms of say for example, the internal energy, say UR is changing so slightly that the temperature of the reservoir remains fixed. So, so basically, if you see, if delta U plus UR equal to 0, this means delta UR, right? Change in the internal energy of the reservoir equals to minus of the change in the internal energy of the system. But temperature of the reservoir is kept constant. That means so delta UR, that change, the delta UR is an infinitesimal change in energy, which basically does not change the temperature of the reservoir. It remains constant because reservoir is infinite compared to the system. So TR remains fixed, right? TR remains fixed always. So if that is so, delta SR is delta UR by TR, which is minus delta U by TR. So from the second law, delta S plus delta SR is greater than or equal to 0 implies then that delta S minus, right? Because delta SR is nothing but minus delta U by TR, which is minus delta U by TR is greater than or equal to 0. Now, delta U by TR minus delta S is less than, that means is less than or equal to 0, which means delta U minus TR delta S is less than or equal to 0. Now, if T equals to TR, right, we are telling that the system assumes the temperature of the reservoir, right, at thermal equilibrium. So, T equals to TR. So, if T equals to TR, instead of TR, I can write T, right. So, then because delta U minus TS is less than or equal to 0, or U minus Ts, as we know, F equals to U minus Ts. Now you can see this basically. So basically, as you can see here, if you start with this, delta U plus UR equal to 0, or delta S plus delta S are greater than equal to 0, basically gives you this condition that delta F has to be less than equal to 0. And delta F is equal to 0 only when the process is reversible. Right? Okay. So if you look at that, so if you look at a closed composite system now, you have this knowledge now. You have the sum of, so you have the subsystems M. There are M subsystems. So for each subsystem, you have some volume. So and the summation of these subsystem volumes is equal to the total volume. It does not change. Then summation of if I do summation of components, so basically here this will be NC, right? So it will be N, right? Where C is basically it can be like this. C is, this is small c, which is basically represent instead of C. Yeah, C is fine. So this is small c. Now small c can be capital A. Means capital A is the component A, component capital B, component capital C, and so on. Now if you have F as a function of the temperature of reservoir, right? It's a function of temperature of reservoir and volume of all these subsystems, right? Because temperature is now fixed, right? Temperature of each subsystem is that of the reservoir, right? So basically that's what we are doing. And then you have Vi, so V1, V2, V3, so on, like V1 up to Vm. Then you have for all components you have NC1 up to NCm, right? And then basically this is the sum of I equal to 1 to m Fi, right? F is a function of the sum of Fi, that is Helmholtz free energy of the subsystems, where each subsystem assumes the temperature of the reservoir, right? It gets the temperature of the reservoir because it's always at thermal equilibrium with the reservoir. So Tf, now the extremation that where we have proved this implies that Tf has to be equal to 0 and T2F will be greater than 0, right? This is the Helmholtz free energy minimum principle. Okay, so in the next lecture we will continue this and we will come to another very important relation called Maxwell relations.